Good morning. In the operating system lecture series, today we will discuss classical problems of semaphore. In the previous lecture, we have discussed semaphore. What are the types of the semaphore we have discussed? There are mainly two types of semaphore which we have discussed. That is the counting semaphore and the binary semaphore. We have discussed the advantages of the semaphore, disadvantages of the semaphore, weight and signals of the semaphore. We have discussed about these things. Now we will discuss some of the classical problems of the semaphore. So let's start. One so the three problems basically we will discuss the three semaphores, classical semaphore problem we will discuss. One is the bounded buffer problem. Second one is the readers writers problem, and the third one is the dining philosophers problem. So let's start with the first one, that is the bounded buffer problem. The bounded buffer problem was introduced in it's, you can say it's a also known as producer consumer problem, is one of the classical problem of synchronization. Let's start by understanding the problem here before moving on to the solution. So we present here the general structure of this scheme without committing ourselves to any particular implementation. There is a buffer of n slots, and each slot is capable of storing 1 unit of data. There are two processes running, namely producer and consumer. So this is bounded buffer problem, is also known as the producer consumer problem. So actually there are the two processes which are running. One is called the producer process, actually producing something, and the consumer process which is consuming something, which are operating on the buffer. So you can see with this figure, there are the n slots in the, which you can say the buffer. This is the producer process which is actually producing the things, and the consumer problem which is consuming the thing. So the code for the producer, the code for this consumer process and the producer process is just producer is to produce and consumer is to consume. Note that the symmetry between the producer and the consumer. We can interpret this code as the producer producing full buffer for the consumer, or as the consumer producing empty buffer for the producer. A producer tries to insert data into an empty slot of the buffer. A consumer tries to remove data from a filled slot in the buffer. As you might have guessed by now, those two processes wouldn't produce the expected output if they are being executed concurrently, since the producer will produce and consumer will consume. So they cannot produce the expected output if they are being executed concurrently. So there needs to be a way to make the producer and consumer work in an independent manner. So the solution of the bounded buffer problem, one solution to this problem is to use semaphores. The semaphore which will be used here, or you can say a binary semaphore M, which is used to acquire and release the log, or empty a counting semaphore whose initial value is the number of slots in the buffer, since initially all slots are empty. Full, so we are using three things: empty, full, a counting semaphore whose initial value is 0. At any instant, the current value of the empty represents the number of empty slots in the buffer, and the full represents the total number of the slots in the buffer. So it was the the producer consumer problem. Now the second problem is the readers writer's problem. So the reader's writer's problem is another example of a classical synchronization problem, and there are many variants of this problem, one of which is given below. So, I will, just read the statement. What is the statement here? One is we distinguish between these two types of processes by referring to these processes that are interested in only reading as readers and to the rest of writers. So there is a shared resource which should be accessed by multiple processes. There are two types of processes in this context. Though there are two types of process, one is readers and another is writers. Any number of readers can read from the shared resource simultaneously, but only one writer can write to the shared resource. So when a writer is writing data to the resource, no other process can access the resource. A writer cannot write to the resource if there are non-zero number of readers accessing the resource at that time. Okay. So before going to the solution, I think you understood the problem, the reader-writer problem. So if two readers access the shared data simultaneously, no adverse effect will result. However, if a writer and some other process, that either a reader or a writer, access the shared object simultaneously, then the chaos may arise. So to ensure that these difficulties do not arise, we require that the writers have exclusive access to the shared objects. So this synchronization problem is referred to the reader's writer's problem. Okay. So now we will see the solution of the reader-writer problem. From the above problem statement, it is evident that the readers have higher priority than writer. If a writer wants to write to the resource, it must wait until there are no readers currently accessing that resource. So while true, wait W, so perform the write operation. So the write operation will have to wait until unless it is not getting the signal. So the writers will have to wait until unless the readers have finished its execution or finished the things. Now the third one is the dining-philosopher problem. So this dining-philosopher problem is again a very classical problem. So consider five philosophers who spend their lives thinking and eating. The philosophers share a common circular table surrounded by five chairs, each belonging to one philosopher. In the center of the table is a bowl of rice, and the table is laid with five single chopsticks. When a philosopher thinks, he does not interact with his colleagues. So, from time to time, a philosopher gets hungry and tries to pick up the two chopsticks that are closest to him, and the chopsticks that are between him and him left and right neighbors. So a philosopher may pick up only one chopstick at a time. Obviously, she cannot pick up a chopstick that is already in the hand of the neighbor. So when a hungry philosopher has both her chopsticks at the same time, she eats without releasing her chopsticks. So the dining philosopher problem states that there are five philosophers sharing a circular table and they eat and think alternatively. There is a bowl of rice and each of the philosopher and five chopsticks. So a philosopher needs both the right and the left chopsticks to eat. A hungry philosopher may only eat if there are both chopsticks available. Otherwise, a philosopher puts down their chopstick and begin thinking again. So the dining philosopher is a classical synchronization problem and it demonstrates a large class of concurrency control problem. A solution of the dining philosopher problem is to use a semaphore to represent a chopstick. A chopstick can be picked up by executing a wait operation on the semaphore and released by executing a signal semaphore. So let's say semaphore chopstick 5 is in the array of 5 elements. Initially, the elements of the chopstick are initialized to 1 as the chopsticks are on the table and not picked up by the philosopher. So the structure of this is given as follows. Do weight chopstick I plus 1 mod 5. So mod 5, the next time is divided by 5, and which is the fifth one. Eating the rice, signal if it is eating the rice, signal chopstick I plus 1 mod 5, then it is thinking. Either it is eating the rice or it is thinking. So in this way, this is the solution of the dining problem. In the above structure, first weight operation is performed on chopstick I and chopstick I plus 1 mod 5. This means that the philosopher I has picked up the chopstick on his side, then the eating function is performed. After that, signal operation is performed on chopstick I and chopstick I plus 1 mod 5, means that the philosopher I has eaten and put down the chopstick on his side, then the philosopher goes back to the thinking. So this was the classical problem. There are some references of these, and these are very important. The classical problems. So we should know the what are they and the solution of this. These are the references, and the next topic we will discuss the deadlock, which is a very important topic. Thank you. So here I'm stopping. Thank you, students.